What's up, guys? Let's continue with this mass balance introduction chapter. We're going to do this problem 26, and please, I do ask you to pause the video, read everything, including maybe until here, because this is very it has a lot of information and you need to understand what is a gas absorption. So once you read it, you can follow me through. Gas absorption is commonly used to remove some species from waste gases. So you get a gas here, and you get another gas here. This may be, no, this is a liquid, this is a gas. The gas passes through here, and the liquid takes out all the, let's say, dust and all this stuff that is, let's say, harmful for the environment. Then the liquid goes here, the effluent goes here with the pollutant, and you're going to treat it, of course, and then you can take out here the air or whatever you're using. I think it's a gas, let's just call it gas, goes out to the atmosphere with less concentration of this substance. So that's the general idea. Let's read it. The waste gas is contacted with the liquid solvent in which the potential pollutants are highly soluble. So that's good. The effluent must be highly soluble with the pollutants and the other species. The other species, for example, SO2, or not, SO2 must be removed, but many other, for example, I don't know, oxygen, nitrogen, they go out. They are not soluble. The clean gas is discharged to the atmosphere. As I told you before, the liquid effluent may be discharged to a waste lagoon or subject to further treatment. I will say this is better, further treatment. That waste lagoon doesn't sound so ecological. And the solvent and or to convert the pollutant to a species that can be released safely to the environment. Yeah, so this must be safe to the environment, and this must be safe to the environment. This one goes to the atmosphere, this one goes to another treatment, hopefully, or worst case scenario, they go to waters and rivers. A waste gas containing SO2 from maybe, I don't know, hopefully you know, it's a precursor of acid rain, and several other species, such as designated as A in general, so A and SO2 are bad for the environment, are fed to a scrubbing tower, which is this one, the scrubbing tower, and it contacts a solvent B that absorbs SO2. So this B is going to absorb A and SO2. Okay. Okay. I know they only tell you it only absorbs SO2. Okay. So A must be the non-harmful gas. So that's good to know. This is okay, this is not good. The solvent rate of the tower is 1000 liters per minute. So it's here, this value. The specific gravity of the solvent is 1.3, so we are going to relate that to mass and volume probably. And the absorption of A and evaporation of B in the scrubber may be neglected. So as I told you before, A is not going to be absorbed, it's going to pass through here as nothing happened. And evaporation of B, maybe you're, because it's getting warm here, maybe you are evaporating this liquid, who knows? We're not going to neglect that, so that is not going to happen. Now, the gas in the scrubber rises through the series of strays. You don't need to know that so technically. This is more typical of mass transfer materials and separation processes. But essentially there are metal plates perforated with many small holes. So you have the tower like this, and you have this thing very perforated, so gas can pass through, and liquid doesn't go just directly. It stays here, then liquid and gas make contact a lot of time, and you have time for the mass transfer. Okay, but you're going to see that in mass transfer and separation processes. The solvent flows over the trays and through the downcomers to the trays below. Gas bubbles emerge from the hole in each. Okay, yeah, that's what I told you. Then the volumetric flow rate of the feed gas is determined with an orifice meter, which is a equipment to measure volumetric flow. And okay, they use pressure, blah blah. They give you this calibration. So for every H value, you get a volumetric value. So that's good because imagine being there and you read, I don't know, 100 millimeters. The operator or the person in charge there can say rapidly, you have a 142 cubic meter per minute flow. Okay, so you need that table. Now, the molar density of the feed gas, which is essentially the amount of moles per volume, or in this case, the amount of moles per liter, it's given by this relationship, 12.2 times P divided by temperature. They must be absolute. And okay, they measure, you have another thing, electrochemical detector, which measures the concentration of SO2, but you have it in this equation. So you have it in moles, molar fraction of Y depends on R. And they tell you it's a rectangular scale, so I don't know, maybe you find the value of R and you can say how much is it in Y. You find a value of R2, they give you Y2, etc. So we're going to use two equipment to measure volumetric flow rate and molar fractions. So the following data are taken: temperature, pressure, the height of the orifice meter, and two measures of R. One in the inlet probably, yeah, feed gas, and the other one in the outlet. So thanks God we're done with all that. This here is only explanation, how does it works. This here is more about the technical data, and finally the volumetric flow rate stuff here, and the molar fractions. So first of all, draw a diagram and completely label a process flow chart, including flow rates, molar flow rates, and SO2 mole fractions of the gas streams, and yeah, essentially everything. And not only that, show that the scrubber has 0 degrees of freedom. So let's do that. Let's first do the diagram. That means letter A. I have this here. This is the liquid. Let's say it's let's call it B0. It's 1000 liters per minute. It has mole fraction of 0.1. It's pure B. And then you have Y1 SO2. I'm going to call S SO2, and A all other gases. So 1 minus Y1 must be A. And here we have a volumetric flow and a molar flow. And it goes here as N3. This will be N2. What is it there? N4. This is Y3. Y3. This is also S and A. And X4, because it's liquid. X4, S, and A. I'm going to call this N4. And this will be N2. Let's say N2. Okay, so I have my diagram. I think I have all the mole fractions. Yeah, essentially, oh, this is not A, this is B. You're mixing liquids and liquids. This is gas and gas. So don't forget that, guys. This is liquid, liquid, this is gas, gas. I'm going to let that so you don't forget. And yeah, you can start doing, let me write this. B is the solvent. So well, I think we're done. Let me just add some data. The temperature, maybe temperature operates 75 Fahrenheit. Pressure is 150 psi G, which means gauge. We will need to add 14.7 to make that atmospheres. And yeah, let's do the analysis of the degree of freedoms. my DOF analysis. Let me count all the unknowns. Sorry, it's of course N1, N3. Let's use, okay, either going to use smalls, okay, N4, N2, N4, volume 1, M2, okay. Well, we could use M2, M4, X4, Y1, Y3. So 3, 6, 9, 10. We have 10 unknown variables. Mass balances, we have n equals to 3, which is A, B, and S. So we can do 3 mass balances. We have also 2 analysis data, which is 2 data for R, which is -2. They will actually give me Y1 and Y3. So let me put it here. Now, with the orifice meter, that will give me the volumetric flow rate. So I got another one going for there. Now the density formula, or the density data relationship, will take me out another one, yes. And the specific gravity will help me to get all the values. Okay, we are 5, 6, 7, 8. And for these two, either we know we can relate by molecular weights. So we can have 2 here. Okay, nice. So I think we're done with molecular weights, relate moles and masses. So 3, 5, 6, 7, 8, 9, 10. So we have 0 degrees of freedom. We can solve it, which is nice. That's perfect. And yeah, let's do it. Letter B, determine the orifice meter calibration formula by plotting. Okay, this I will not include it because it has nothing to do with mass balance, even though I will give you the formulas. So you should get this value here. I don't like to give you this because this is actually, I cannot imagine a professor giving you this in exam. Makes no sense. I will prefer you to show me that you know how to do the mass balance rather to use math. So this is the first one, question number 1. And for the mole fraction of SO2, I got 5 times 10 to the -4 times exponential ER. This is equation number 2. So that will be letter B. Letter C is calculate mass fraction of SO2 in the liquid effluent stream. That's very easy. And what else? The rate at which SO2 is removed from the feed gas. So yeah, let's do it. That will be X4. So in the effluent, you might be thinking that C1 is easy, it's just to plug some data here. But no, guys, this is only in the gas. And we are asked for the effluent one, the one which is liquid one, X4. So we will need to do, for X4, we need to do mass balances. Yeah, I'm sorry guys, you cannot get that directly. It sounded so easy, but it is not. So yeah, essentially let's do our mass balance here. Will be, first of all, I'm going to get my volumetric flow rate in the inlet given R. So times 210 to the 0.55, because R is 210 here. This is in the inlet, so I used this, and this is 207.3 cubic meters per minute. So I got that in the inlet. So fast I got it. Now I'm going to relate the density moles per liter to mass. Well, essentially first to moles. I'm going to use the volumetric inlet, then I'm going to get moles and maybe molecular weight. I get mass. So yeah, what do I need for that? Let me go to the formula. It's here, 12.2 P times T. It's mole per liter. 12.2 P divided by T. 12.2. What's the pressure? Pressure, I need it in, what's the units of this? I need it in atmosphere. So let me change the pressure, which I got here. Where is it? Pressure equals 164.7 psi absolute. So let me go. Let me change that to atmospheres. So this is the conversion factor. And the temperature is 75 Fahrenheit. I think I need it in Kelvin. Yeah, I need them in Kelvin. So 75 Fahrenheit minus 32 Fahrenheit divided by 1.8 Fahrenheit. That's Celsius plus 273 to change it to Kelvin. So my density is essentially 12. Let me show how much I got here, so you don't get lost in the calculations. That's my density. 45 mole or kilomole per cubic meter, which is essentially the same as 0.45 mole per liter. So nice, I got my density. Let me write it here. Density is 0.45 kilomole per cubic meter. Now let's continue with the next step, that will be calculate the amount of moles. So that's my mole flow, will be essentially this times this, 0.45 kilomole per cubic meter times the volumetric flow rate. Where is it? Here, 207. So yeah, probably you're asking why I changed it to kilomoles per cubic meter. It's because I wanted to cancel these cubic meters. Doing this operation, I got 93.3 kilomoles per minute. That's my molar flow rate going in the inlet. So this guy here, where is it? Here, it will be N1. So this is N1. What else can we do? Okay, let's use formula 2 to get all the values of y1 and y3, which, if you remember, I told you here, it's actually here. With the data of R, we can get y1 and y3. So let's use this equation. Bring it up here. I got for R1 equals 82.4 and R2 equals 11.6. Y1 will be 5 times 10 to the minus 4 and multiply the exponential of 0.06 times R. Okay, this is 0.07. That's my first value. Now let me calculate y2. 5 times to the minus 4 exponent 0.06 times R, which is 11.6. I got a smaller value, which is my y3. So very easy, we got our mole fractions in the gas, which is, let me go to here, it's the mole fraction here and the mole fraction going here. So you can see y1 and y3. Let's continue with the problem. Slowly, but we're getting a lot of data. And yeah, essentially, we need to do the mass balance. Let's do it over A. It's a molar mass balance, and it's equal to inlet equals outlet. There is no production, no consumption, and no accumulation. So yeah, over A times N1. This is the inlet. We go here. This is the inlet of A, so that's why I'm using this value. And the outlet is only this one, and of course is this value. So it's very easy, that's why I'm doing it. It's 1 minus y2. You're asking why I'm doing it over A, because it's the easier form to, or easiest way to get N3, because we got everything. It's 3, sorry. 1 minus this value, which I already calculated, N1 I got it was 93.3 kilomoles, equals 1 minus 0.001 times N3. Solving for N3, one equation, one variable, it's easy to get 88.7 kilomoles per hour. And yeah, we got now 2 molar flow rates. What else can we do? Let's do, actually no, we haven't answered our question. We're going to do our mass balance in SO2. Here we go. Since it's only the gas, we're going to do it here. And we have 2 outlets, guys, here in the liquid and in the gas. So take care. Let me do that. It's the inlet equals the outlets. How many inlets do I have? Only in Y1 and 1. And outlets I have 2, in Y2 and 2 of course, and Y3. I have what, N2 and N4. Well, let me just be sure, what do I call it? I call it N4, sorry guys. So it's Y3, N3 plus Y4, N4. So I got Y1, yes, I just calculated over. N1, yeah, it's 80, how much was N1? 93.3. What else do we have? Y3 is 0, yeah. N3 is 88.7. Y4, no, I don't have this. Y4 and 4, I don't have it. So what can we do? Let me just give you this little trick. What's this amount, guys? This amount is the amount of SO2 in stream 4. In stream 4, what is? It's a liquid. Yeah, it's a liquid. Well, essentially it's X. Sorry about that. It's X. SO2 in 4 or in the liquid. So that's the total amount that will be, you do this is moles of SO2 in liquid. So let's see how much moles do we have of that. I got 6. I got moles of SO2 in liquid equals 6.56, which is X4 and 4. Okay, so why do I want this? Because I'm jumping into the conclusion that they asked me the rate at which SO2 is removed from the gas. So kilograms of SO2 per minute. I got moles per minute, so why not just use that? This is kilomoles per minute. Let's use that. We need molecular weight of SO2, which is, this one is 32 and this is 16 times 2, 32, 64, yeah, 32. No, yeah, 32. 16, no, let me, no, 32 grams plus 16 times 2, 64 kilograms per kilomole. So if I multiply X4 N4 times molecular weight, I will get the mass of SO2 being removed, which is exactly C2. Let me do that. 6.56 kilomoles per minute, multiplied by the molecular weight, which is 64 kilograms per kilomole, and I get something around 420 kilograms of SO2 being removed from gas, or are now in the liquid phase. So that's C2. It's kind of strange that we got C2 first, then C1, but we need to find C1 still. So let me do it. Mass balance over B. And let's do this. Let's go back here. Let's understand what we are going to do. I'm going to do a mass balance on B1 and 2. This one is very easy. Equals M4 1 minus X4. And how do I get M0, guys? M0 is from density and volume. I have the volume, yes. I have the density, no. I got actually specific gravity. So it's a specific gravity times the density of water. This is the times the volume. So specific gravity was 1.3. This is 1000 kilograms per cubic meter. And the volumetric flow rate was 1000 liters per minute. So let me change that. I need to change 1 cubic meter, 2000 liters. So look how kilograms goes, no, actually no, kilograms doesn't go. Cubic meters with cubic meters, liters with liters, and I get kilograms per minute, which is 13. So, of course, this one also goes away. Kilograms of B per minute. So I got my initial mass flow, which is here. Where is it? Where is it? Yeah. M2 or M0. Yeah, I'm calling it M0. I don't need to get the moles. I don't think so. Normally, when you are doing this type of problems, we let all the liquids in kilograms. We don't use moles. So yeah, M4. How do I get M4? I don't know. So let's call this equation. We need to think a little bit how to get M4 so we can get X4, which is C1. So I remember this equation. Yeah, let's call equation number, I don't remember the number, which number, 2, 3, okay. Equation number 3. Equation number 3, and this equation number 4. So try to solve equation number 3 and 4. We will have to get these. Okay, we got Y4, X4, X4, M4 equals 6.56 kilomole per minute. Or if I use molecular weight, which I already did, X4 and 4 molecular weight, will give me 64, where is it? Yeah, 420 kilograms, so 2 per minute. So I can use this equation 3. I turn it into 5 to solve equation number 5. Actually, since we're using mass, this guy here is M4. So X4, M4 equals 420. Please tell me that you get it. I'm using this N4, which is, let me tell you the units, is moles of mixture divided by, actually no, it's this, yeah. Let me redo this again. Let's structure this as X4 molecular weight times N4. which is 420. We want to get rid of, actually, we went, yeah, to force M4 as M4. Yeah, this is M4, X4 equals M4, and yeah, this will get you 420. So this is my equation 5, sorry, once again. And I can solve now with equation 4. Let me do this, is go up, up. So we got this, and M4 is 420 divided by X4. Let me substitute that here. This was equation number 5. I turned it into 6. Let's substitute equation number 6 into this equation, which had the number 4, I think. Yeah, into equation 4. 100. Okay. So yeah, solving this, you should get x4 equals 124, 4. And this is C1 finally, guys. We got C1. Whew, that was kind of large. Then C2 we got it already. And finally, letter D. Discover column trays commonly have diameters of 1 to 5 meters. And perforation holes on the order of 4 to 12 millimeters, leading to the formation of many tiny bubbles. Okay. Speculate on the advantage of making the bubbles as small as possible. So this is theory. So imagine having this, I don't know, you have 10 millimeters versus a 4 millimeter, and you are doing this, gas is going through here, and you're going to get this bubble. This is gas bubble. And this is the gas bubble. But per unit space, so let's say you got only 1 square meter, you're going to get, I don't know, maybe 100 bubbles at 10 millimeters, and in the same space, the 1 meter square, you will have, I don't know, maybe 500 bubbles at 4 millimeters. So I will prefer to get this one because little bubbles mix better with the liquid, which makes a better mass transfer rate. This is typical mass transfer theory, guys, so you don't care or you don't get it, it's okay. Since the liquid goes through, this is the liquid, this is pure B, and then it's going to get mixed in the bubbles and take out all the S, so at the end I got B and S. And this gas, let's say it's entering here, it's going out here. This is gas A plus S, very rich, and this is A plus S, very poor, because the S is transferring to this part. So hopefully you get that idea. I'm not going to explain that much because that's mass transfer theory. If you are really interested in this kind of processes, go to my course. Eventually I'm going to upload some courses on mass transfer. And yeah, essentially it's everything, guys. It's a very large video, very large procedure. I think the tricky part here is this part here, to know that this is the amount or moles of SO2 in the liquid. And the other part I might be mixing you is how to transform. You got X4, N4, and MW. This is given in mass fraction. This is mole flow, and this is molecular weight. So how do I change this to mass flow? And times mass fraction, you know, mass fraction and mass flow, we can do that. And yeah, just that's the trickiest part, I think, but everything is about mass balancing. And the degree of analysis is here. As you can see, we could solve it, and we did solve it. And yeah, see you in the next video, guys.